This presentation is really aimed at researchers who do scientific visualization, who do scientific rendering, and not so much at people who are already doing animation and photorealistic rendering. So I'm going to talk today about ParaView and OSPRay, but there are many other packages, things like Blender and others that will let you do photorealistic rendering. And if you're familiar with these, you already know, a lot of the stuff that I'm going to show you today. But today's talk is really aimed at people who want to do photorealistic rendering in ParaView and perhaps Visit and VMD. And I'm going to show you how to do that, at least in OSPRay. Okay. So scientific visualization applications, packages like ParaView, Visit, VMD, they're all written with OpenGL. So OpenGL is a popular library for computer graphics and hardware acceleration. So doing computer graphics and visualization on GPUs, graphical processing units. And so OpenGL has been around for a while, since the early or mid-1990s. And it's an industry standard. So typically, OpenGL is implemented inside a driver provided by the vendor of your GPU card. So for example, an NVIDIA driver. And ParaView will call OpenGL functions, library functions, and then these will be executed by the driver, right? So the calls go to the driver, and then the functions run on the GPU. Alternatively, there is also Mesa. So Mesa is an open source project. Sometimes it's called Mesa 3D. It's an open source project to implement the same functionality inside software. So software running either on GPU or CPU, but open source software. So Mesa is an open source project that tries not to rely on any proprietary drivers. So if you're running a ParaView so it will call OpenGL functions, and then if you're running it on top of Mesa, then Mesa can either run on top of GPUs, so execute these functions on a GPU, or it can also do it entirely in software on a CPU. But in either case, all functions are called via, all rendering is done via OpenGL, whether it is rasterization, so rendering polygons, or ray tracing. So more recently, you also have an option in ParaView, Visit, VMD to use ray tracing library called OSPRay. So OSPRay is an open source library from Intel that's been around for about 5 years now. And it was implemented incorporated into ParaView 5.1 about 4.5 years ago. And it runs entirely on CPU, so there's no GPU involved. It's really fast library. It makes use of all the recent developments in Intel software architecture, and is built on top of Embry low-level ray tracing kernels. So it's really fast, can run actually faster than the more traditional Mesa software renderers. And it's also very efficient when it comes to memory. So on a single workstation laptop, it can handle quite easily hundreds of millions of triangles and billions of particles. And also it can work with non-polygonal surfaces, things like cones, spheres, etc. And because it is ray tracing, it actually provides very nice images with ambient occlusion, where light is bouncing off the surfaces, and the light, the shadows are computed properly. And as I mentioned, it's already included into ParaView, into Visit, VMD. So back in September 2016, so almost 3.5 years ago, I gave a presentation on OSPRay. And I showed some images, so there are just a couple of screenshots from that presentation. And as you can see, OSPRay can actually provide really nice-looking images. So it can highlight very intricate scenes. If you have, either surfaces or streamlines, it can actually show you shadows, and it will give you a more realistic-looking visualization. So the conclusions that I had back in 2016 about OSPRay is that it's really nice. It works great. It's a much faster, factor of 5, 6 faster than other software renderers inside Mesa 3D. And it's almost fast as OpenGL for exactly the same scene. So OpenGL running on a GPU is almost as fast as that, but you're doing all your rendering entirely on a CPU. So OSPRay worked back in 2016 really well already for surfaces and volumes. So the only problem I had three years ago is that I could not make OSPRay work in parallel on MPI. So now fast forward to 2020, MPI backend works really well. I'm going to show you an example at the very end of this presentation where I ran OSPRay on a cluster using MPI, and it scales beautifully across multiple cores and across multiple nodes. So now also you can use OSPRay in client-server mode. So the only thing is that you have to have the version of ParaView server that has OSPRay built in, and we do have such a version at least in Cedar cluster. And now you also have a choice of renderers inside ParaView's OSPRay. So in ParaView 5.7, you can actually enable two different renderers. One is called OSPRay Raycaster. So in earlier versions of ParaView, it was called Sideways Renderer. And then the second one is OSPRay Path Tracer. So the first one, Raycaster, can compute. So the pictures that I showed you in previous slide, they were all done using Raycaster. And it can compute, surface volume rendering, do ambient occlusion, so light will be bouncing off hard surfaces. It can optionally do hard shadows. But in ParaView, as far as I know, in ParaView, this OSPRay Raycaster renderer cannot use materials. But if you switch to the other renderer, OSPRay Path Tracer, it can actually render realistic materials. So this is what I'm going to talk about mostly today. And if you're running ParaView on top of, if you have an NVIDIA GPU on your laptop, then you will actually see a third option. And the third option is CUDA-based optics. So that third option is also ray tracing, but it's not OSPRay ray tracing. It's ray tracing that will run on top of a GPU using NVIDIA's optics commercial ray tracer. So it's closed source. It's not open source, unlike OSPRay. So this presentation was actually inspired by a December 2018 blog article on doing realistic rendering with ParaView and OSPRay. So this was published on the Kitware blog. Kitware is the maker of ParaView. And there they have a nice rendering where they have a power plant, some engine or some machinery that they did. It's a movie, actually a 20-second clip that they did using OSPRay. And it looks fantastic. So the nice thing, the interesting thing about it is that it was done not on a single CPU. It was actually done on a cluster, on a large virtual machine inside Google Cloud. They used 72 virtual CPUs, and it took 35 hours to render. So it can, OSPRay can produce nice results, but it can take a while because, well, you have to do all this rendering in software. So if you want to take a look at this rendering, and especially if you want to reproduce it, I actually find an online presentation that is linked from the slides. This presentation at the bottom of the slide, ParaView and OSPRay walkthrough by Aaron Knoll and Bruce Cherniak from Intel. And they actually, in their presentation, in the slides, they actually have a link to the data set and the detailed walkthrough how this visualization was done, if you're interested in this. But I'm going to show you something much simpler than this. I'm just going to show you an example with a single object, and then I'm going to turn on ray tracing and assign an OSPRay material to it. Before I run into any demos, I'm going to show you a few slides just showing you how we do that step by step in ParaView. And the reason I'm not showing you live ParaView right now is because I'm running this video conferencing on my laptop, and it's using all the CPU cycles. So when I try to run ParaView at the same time on my laptop, it's going to be very slow. But I'm going to try it anyway in a few minutes. So when you start ParaView, you can bring up the plane source. Simply go to Sources and then Plane and click Apply. And that will create a two-dimensional plane. And by default, your view is going to be two-dimensional. So what you want to do next is switch to 3 dimensions, right? And then click on one of the predefined orientations so that you actually see the plane. And then you can spin it around in 3D. So you will have a nice 3-dimensional object. So make sure that it's positioned on the bottom. So this will be a surface on top of which we're going to be building our objects. And then you want to assign some texture to this plane. Because later on, when we turn on ray tracing and we have refraction, you'll actually see some nice patterns, and you want to assign some pattern to this plane in the first place. So if you click on, with this plane already defined and showing in your visualization view, if you click on Information panel right here, you will see that there are already texture coordinates that are defined for this plane. So whenever you use the plane function inside Sources in ParaView, it already computes the texture coordinates for you, which is nice. So you don't have to compute these yourself. If for some reason you have an object in ParaView that does not have texture coordinates, then you can actually, there are a number of filters that let you compute texture coordinates for a flat surface, for a sphere, and I think for a cylinder. But then you have to pass your object through this filter, and then we'll have texture coordinates into which you can load an image, a bitmap image. So let's load the bitmap image into our plane under properties with the plane loaded. You will scroll down, and under miscellaneous, you can under texture, you'll see a drop-down menu, and there you will click on it, and one of the options will be load. That will open a file manager, and you can choose the pattern that you want to load. So I included the file checkerbox JPEG image into the zip file that contains the slides, and so you can actually experiment with this after the talk on your own. So after you loaded the texture, it appears nicely in the visualization window. And next, you go to sources and bring up a sphere object, and then modify properties so that the sphere sits on top of the plane. So basically, what I want to do is you want to offset it by some, Z offset, and the Z offset should be equal to radius so that it barely touches the plane. Then make sure that the theta and high resolution are sufficiently high so that you have a nice round sphere. And then if you scroll down in properties all the way to the bottom, you'll see a button enable ray tracing. So click on that, and that will switch from default OpenGL rasterization to ray tracing on a CPU using OSPRay. And then right below that, the back-end drop-down menu, make sure you choose OSPRay Path Tracer. Okay. And as I mentioned before, the Path Tracer can let you define materials. So in the same, if you scroll a little bit up in the same properties dialog, you will see a drop-down menu for materials, and there you can choose glass, and then the sphere will appear as a glass sphere. You see nice refraction, and you see that it's now you're doing photorealistic rendering. So the quality of this rendering is going to be fairly low because you're just doing a single pass, but optionally, if you want, you can increase the quality. So right below the this backend dialog, you will see samples per pixel. That is, default is 1, and you can set it to high values. So let's, for example, 10 or 30. So for production visualizations, I recommend something like 30. But if you're just playing with it, it can be as small as 1 or a few samples per pixel. And then if you set it to a higher number like 10, then it will take a while to render, so 10 times as long. But you will get a lot less noise in your rendering. So I'm going to show you how you can add a second object to the same scene. So now we have just a single sphere, and we're going to add an object from a VTK file. So into the same zip download, I included a teapot.vtk data file. And continuing with the same scene, you can go to File, Open, and then navigate to teapot.vtk, and then load it. Here the trick is, if you want to this teapot to appear nicely alongside the sphere, you have to change its scale, so its size, its orientation, its origin. So basically play with this and make sure that you see both objects at the same time nicely. So I had to change the, to reduce the scale, the size of the teapot quite a lot. So it's roughly the same size as the sphere. And also spin it by 90 degrees around the Z-axis. And then also modify its, so offset the origin, the position of the teapot. And then next, I'm going to click on teapot in the pipeline browser, and then scroll down to material. So you already have OSPRay turned on, and then switch to another material. So in this case, I picked scratched, which is a metal type material. So it's metal surface, and it's scratched, so it's kind of a rough metal surface. And then finally, I again make sure that I have a high number of samples per pixel, for example, 10. So these things actually appear nicely. Okay, so that's all I have to do. There's not much beyond that. Okay, so now I'm going to show you actually a live demo. So I will attempt to run this on my laptop. The problem is that I'm running video conference software, so it's actually, if I run ParaView, it's going to be very, very slow, but I'll try anyway. So the way I do this, is sorry to kill my email client. Here we go. The way you do this, if you're on a Unix system, like I'm on a Mac, I can open a terminal and I can simply type ParaView, which is actually, so ParaView for me is an alias for the ParaView application inside the applications folder. So I'm typing ParaView -- state, and then I'm going to type the, I have a pre-saved state file that is called checksphere_tpsm. And this is just to speed things up, so I don't do things from scratch. And that will open ParaView. Here we go. And then it will load all the data sets, all the stuff that I showed you in the slides before. So here I'm doing live rendering with OSPRay. And it's actually, so if I try to spin it, you will see that it's a little bit slow, but it works because, well, ParaView now has only a small fraction of the total number of CPU cycles, but it works. So if I want to speed it up, so if I want to make it more interactive, what I can do is I can turn off ray tracing. So I just scroll down all the way to the bottom in properties. It's actually really slow. And then I turn off ray tracing. So here we go. Now I'm back to OpenGL rendering, and it's a lot smoother, right? And this is the general theme for today's presentation. If you are setting a complex theme, especially if you're doing an animation, then what you really want to do, you want to switch off ray tracing, go back to OpenGL, which is going to be a lot faster because, you know, it doesn't do realistic surfaces, doesn't do shadows, etc. And then set up your animation or set up your final scene, and then when you're happy with it, switch back to ray tracing, and then it will do the OSPRay ray tracing. It'll be somewhat slower, okay? And then here you see that I have samples per pixel, which is 1, so I have a lot of noise here. And then I can actually increase it to a larger number, let's say 10, and that will produce much nicer objects, but it will take a few seconds for this. So with samples per pixel set to a high value, your rendering stops being interactive, right? Because it's going to take, you know, a while to render each frame. If you want to still have high quality but interact with it in 3D, what you can do is instead you can play with progressive passes. So I'm going to show you in a second once it starts computing this 10 samples per pixel. Once again, this is really, really slow only because I'm running video conferencing right now. Okay, so now you see that I have a nice sphere and a nice teapot without too much noise. So what I'm going to do now is I'm going to kill ParaView. And here I'm going to use the same command line to load the same ParaView state file, but I'm also going to add an option, enable streaming. And what this will do, it will actually let me process the same scenes in multiple passes. So let's wait until it loads the scene. Here we go. And then I scroll all the way to the bottom in properties. Okay, all the way to the bottom in properties, and then I set progressive passes to a high number, let's say 30. And what this will do, if I'm not interacting with the scene, if it's just static, I'm not rotating or zooming, etc., it will do multiple passes, and the image quality will increase as you're looking at the image. But I can actually start interacting with it, and then it will do a low number of passes. But as soon as I finish interacting with it, it will start computing more and more passes for a static scene, and then these will give you both high quality and interactivity at the same time. But again, now it doesn't work nicely because video is stealing all the CPU cycles. Okay. I see there's a question in the chat. Does this require ParaView 5.7? 5.5 is okay. So OSPRay was included into ParaView starting from 5.1. So you can use it in 5.5, but in 5.7 there's a lot more functionality. So I suggest you use the latest version just to use all the latest functionality. But it is included into 5.5. All right. So OSPRay materials. When you download precompiled ParaView, you already have a material options not available in 5.5. Okay, yes, this could be very much true. So because in 5.5, so in 5.1 you had OSPRay since 5.1, but the path tracer that I mentioned a few slides ago, it might have appeared only in 5.6 or 5.7. So that I don't know when it appeared exactly. So you might be, you will be able to use OSPRay in 5.5, but not maybe not the OSPRay Path Tracer renderer. So you might be right. Okay, so when you download precompiled ParaView, it already includes a bunch of materials, and these you can find inside the binary installation, well, inside the precompiled ParaView installation. So this slide shows you where you can find these. So it's a JSON file, JavaScript object notation file, that you can find. Here's where you find it on a Mac. So just drill into the applications, ParaView application folder, and under materials directory, you will find this JSON file. And then here's where you find it on Linux. Where you can find it on Windows, I don't know, but it should be there. Should be there somewhere in the installation as well. And so when you click on materials in the drop-down menu, so the materials that you see there, this selection is these are only the materials that are defined inside of this JSON file. If you want to use other materials, you have two options. You can either download somebody else's material, so a third party from the internet. So if you go, for example, to, I have a link here to a nice database of several hundred materials that somebody posted on ParaView discourse forum, and it's a really nice database. I'm going to show you an example later on. Or you can create your own materials. So creating materials is actually not that difficult, and if you understand how to do that, it will actually give you a lot. It will give you a lot of power because you can define your own materials and you can modify existing materials, etc. So there is quite a good documentation with the OSPRay project for materials. Here I have several links. So the first link is the best. If you go there, OSPRay materials reference on the GitHub page, it will actually give you a lot of useful information. And oops, sorry, it will give you a lot of useful information. Yes. So let's see. I'm actually missing. Yes. So this is this is the slide I want to show next. So the OSPRay materials, these are the OSPRay materials you can use in ParaView. So object material is one of the most common ones. It's the workhorse material. Principal is the most complex material, and it's actually used for rendering non-traditional, well, unusual surfaces, so things like plastics, etc. Car paint is a specialized version of Principal for rendering different types of car paints. Then there is also metallic paint. There is metal for rendering physical metals. Alloy is similar to metal, but it has much easier to understand color control parameters. Then there is glass, thin glass. And all of these take in parameters. So I'll show you some examples in a couple of slides. And some of them take as many as several dozens of parameters. So these materials can actually be customized, fully the way you want. And many of them also allow textures. I'm going to show you examples very soon. So I wrote here a simple script to test different materials. So in the script, what we do is I create a plane, then I load texture into this plane, and then I create a sphere sitting on top of the plane, and then I assign some OSPRay material to this sphere. So the problem with I had when I was working on this script is, of course, like everybody else, I used the ParaView trace tool to create this script from the GUI actions. The problem is that loading the ParaView materials, so that option number 2, when in ParaView, when you go to File, Load Path Tracer Materials, that option can actually not be translated by, it does not get translated by trace into Python script, so I don't know why. But I had to use a hack. So essentially what you can do is, instead of loading materials that you define yourself from a file, you can actually modify the file, the materials file inside of the ParaView installation. And that way you can modify materials, existing materials, introducing new materials, etc. So basically what you do is you modify this OSPRay materials JSON file, and then you run the script. So you'll say pv batch, which is the usual ParaView command for writing for running an existing script. So you say pv batch test materials.py, and then here you pass 2 arguments. The first one is the name of the file with the texture that you're going to put into the plane. and then the last argument is the name of the output image, right? So you run the script, it will create a local image, and then you open this image. So here are some results. I played with several images. The first example is a wooden texture. So I use the wood material, which is actually one of the default materials inside that JSON file. So it's a type object material, and it doesn't have any parameters. It basically loads the texture for the wood. So one problem here, and I don't really know how to solve this problem. One problem here is that wood JPEG is a JPEG image of a wooden surface, so it's a texture. So when you load it, the same texture is going to be applied to all polygons in the sphere. And if you have a high resolution sphere, then the polygons will be very small, so you actually will not see the wooden pattern because it's so small. So this is why for this sphere, I actually had to decrease its resolution, so you actually see some traces of the texture. I don't know how to solve this problem for this sphere. Obviously, this problem will not exist for large surfaces because, if you have for large flat surfaces, if you have a large flat surface and you load a texture into it, well, the texture will be large, so you'll actually see the pattern yourself with the naked eye. The second example is scratch material. The same example I applied to the teapot earlier. And here you have one parameter that's metallic. I don't remember what it is. I played with it, but I don't remember now. You can play on your own. And then there are a few textures that are loaded into this material. So basically, it's a metallic surface that has several layers, and it gives you, this nice image with reflection and highly reflective image. So the next one here, I'm just creating my own materials, thin metal. Basically, I copied Scratch, the previous example, and then I assign some transparency to it. So opacity is 0.5 instead of 1, and also I give it some sheen. So sheen is brighter appearance towards the edges, right? So you can see that at the edges it is brighter. Next example is gold. So gold is a physical metal, and here you define the refraction index in 3 colors, so red, green, and blue. So eta is the real part of that refraction index, and k is the imaginary part. So I can't really explain how k will affect your image, but it will. So you can play with it on your own, and you will see the result on your laptop. And then we have roughness, which is 0.2, so it's kind of a rough surface. Next, I have car paint. Another car paint, just 2 different examples. And in the second car paint, as you can see, I have flakes, so it will give this kind of a rough appearance, and it looks, I think, really, really nice. There's a question: can OSPRay materials be imported directly into ParaView? So the answer is yes. I have not played with it, but I saw some discussion in ParaView discourse on how you can bring in materials from other sources into this format. So basically, we'll have to convert it into this JSON format. And I saw some examples of doing this. And they mentioned several different formats, I think, including OSPRay. But the answer is yes, you can, but you have to Google it yourself. Then the next example, glass, which is the standard glass material. So I don't modify anything here. The next one is green glass, and then green glass is I just take the same glass material as before, and then I set up RGB, so 3 colors attenuation, and then also modify. Actually, there's a type here. I should modify this to 2.5. So eta is the refraction index, and it's 2.5. So you can see actually refraction is slightly different from the previous glass example. And the last example material I have on this slide is a thin glass, and thin glass is really meant for rendering thin windows and thin glass surfaces. So what you can do with thin glass is the following. You can actually assign a texture to it, and then if you have a light source, it will cast nice shadows, so you'll have this kind of a stained glass effect, and it's really, really easy to do. So basically, this is the material you have, right? So here you specify the texture that is loaded from a let's say a PNG file. And then you also need to copy that PNG file into the materials directory inside ParaView, and then you run it. So let me show you an example. I'm going to see ParaView, and then I'm going to load the stained glass, I guess. Yeah, stained glass state file. So let's see if it works. I'm getting some keyboard typing from somebody, so please mute yourself. All right, so here's the visualization, and as you can see, it is live, it is interactive. Also, it's very slow. And so here I set up a light which is sitting to the right from the scene, and it casts this nice shadow. And the way you set up lights in ParaView is you have to go to View and then Light Inspector. And it's not exactly intuitive because you have to, unlike in Visit, you actually have to type in the properties of the light by hand. But here I enable a second light, and you can see that it's a directional light, so it's a point source light that is sitting from the right from the main scene. Okay. All right. So far, we had multiple objects inside the ParaView's pipeline browser, and to each object we were assigning a unique material. So a glass had a sphere had a glass material, and then the teapot was scratched metal. But you can also assign materials based on a value of a scalar field, which is really nice. So, for example, if you load a multi-block data set, you have different parts or different blocks in this multi-block data set, and then each part will have a variable that is typically called either block ID or region ID, and then you can assign material based on that value. So I'm going to show you an example towards the end of this talk where I have a complex scene downloaded from the internet, and then there are multiple regions with different block ID variable, and then I assign different materials to different values of this variable. So the next example is on the same topic, but much simpler example. So here I wrote a Python script. So it's a standalone Python, so ParaView's Python, just Python 3, that I run totally independently of ParaView. And it loads NumPy and another library that is called PyEVTK. And this is really fantastic library. So I use it almost daily, really useful. And what it lets you do is you can write VTK files from this library directly, independently of the main VTK library. So the VTK library has a Python interface, and it's really great, but it's quite heavyweight. You have to compile it yourself, and it's it's really fantastic. It's very powerful. But PyVTK is much simpler. It's very easy to install. Usually installed by Conda or Boo or Pip installer, and it's super easy to use. So here's the entire code. And as you can see, what I do here, I define 3 objects. So basically, I define a cube, a cubic cell, then a tetrahedral cell, and another tetrahedral cell. And what I'm doing here, I'm passing the arrays x, y, and z. And then, so there's a single array x, y, z that contains the list of the x, y, and z coordinates of these of all the vertices in these 3 objects. And then I also have a connection array. So connection array just contains a list of vertices. So it simply says 0, 1, 2, 3, and all the way to 15. I have 15 vertices in total. Then I need to provide an offset array. And this is important so that ParaView knows where each cell ends and the next cell begins. So basically I have 3 objects. The first one has 8 vertices. Next one is a tetrahedron with 4. Let's say 4. Is it really true? It should be more than 4. Anyway, yeah, I'll double check. But anyway, so these are the ending indices of. So this is the index of the last vertex in each cell in my scene, and then I supply C types. So C types is basically the type of a cell. So I have a hexahedron, so which is a cube, a tetrahedron, and another tetrahedron. And then here, so this is the important part. I assign density. So I have 3 objects, and then I assign a variable called density. It's equal to 1 for the cube, 2 for the first tetrahedron, and then 1 for the second tetrahedron. And then I simply write these data structures to this into a VTK file called cells.vtu. So I run the script. I'll simply say Python create cells.py, and that will create a file cells.vtu that will load into ParaView. So when I do that, I will see 3 objects. So I see 2 pyramids, 2 tetrahedra, and a cube, and I can actually assign materials to them. So this slide shows you how to do that, but I'll actually do that live, so you can actually see how I do it inside of ParaView. So it is initial, what is called cells initial. So here I'm loading my objects, my scene. And as you can see, there is a plain object, but that's just the texture at the bottom. And then there is a single object that contains my 3 cells. And that object is the cells view BTK file right here. So I click on this file, and then I scroll down in Properties. And then, so I already have enabled Ray Tracer, and then OSPRay Path Tracer. And then I scroll a little bit up. And where I choose the materials, I'll say, instead of choosing one of these materials you saw before, I choose value indexed. Okay. Then I open the edit color map dialog. And then actually, before I do that, I need to switch to the density variable. So I color by the density variable. Okay. And then I go to edit color map dialog. And then I click on interpret values as categories. So those values where density is equal to 1 is a single category, and then the next category is density equal to 2. And then I send materials. So the way I'm going to do it, I'm going to say 1 is will be shown as gold, and then 2 is going to be shown as, let's say, I don't know, aluminum. Okay. So here I have aluminum at the bottom. Right? And then 2 gold objects. And if let me enable a high number of samples, and I need to go back to Properties, scroll all the way down, and have, let's say, 5 samples, and that will produce a much nicer picture. So the bottom line here is you can actually use a scalar field, a scalar variable, to differentiate between different materials in the same object, which is really nice.
Sorry, it may be because the stream is lagging a bit, but how did you get the annotation to apply a material to the object if it's just, it looks like just a text field? Like if you were to type in garbage, it's not going to apply.
Yes, exactly. It has to, so basically when you type the annotation, when you say gold, it will look to material called gold inside the JSON file. And if there's no such material, it will simply use the default, it will not use any material. So yes, the annotation where you type in the column map where you type gold here, if you type something else, let's say gold, right, something like this, it will just not find that material. And most likely what it will do, it will switch to no material. So let's just see. Here we go.
Okay. Okay, so as long as the annotation is defined in the JSON file for materials, that's fine.
It will give you that material, exactly. And then you can define your own materials the way I showed you before.
Okay. Exactly. On that note, can you use multiple JSON files? Is there any way to kind of segregate your?
Yes. So I don't know how to do it from ParaView Python script because I don't know the function to load a JSON material, well, OSPRay materials from a JSON file. I could not find that. I was looking for it, but I could not. So if you want to do it from ParaView Python, what you will have to do, you would have to basically put all materials into the same JSON file. But from the GUI, you can. So from the GUI, actually, it's a good point to show it now. So let me, again, have just one sample per pixel so that it's faster. And then I will go to File, and then Load Path Trace Materials. And then here I'm going to load the materials that I mentioned before. So that is one of the previous slides. You can download from the ParaView discourse. And now let me go. Actually, I don't remember what those materials are called. So let me go to, I'll open another terminal window, and I'll just cd into the directory where I have my materials, and it's in this file. So I have to basically pick one of these names. For example, this one. So let me just copy and paste it into the column map and see if it works. It should. Here we go. So that is material that I just loaded from a new file, a standalone file. So in this case, ParaView right now has access to all materials defined inside both the default JSON file and the new file I just loaded.
Cool. Is there then, so that's having multiple materials, which is excellent. Is there a way to have a material that is parametric on some variable? Like you want something that is affected by another value that you define else.
Right.
Let's say glossiness. You want glossiness.
I don't know. I haven't thought about it, and I have not seen any such examples. So what you can do, you can always define your own texture, right? So texture will be representative of a material, but it will not map. It'll just be static texture, so it will not map, one-to-one, right? So it will not be function showing you the actual material distribution. So the answer is I don't know. Maybe not. Maybe yes. I don't know. I've never seen that.
Okay.
All right. So let me kill this ParaView, and then go. Oops. ParaView. And then go back to the slides. Okay, so you can mix scientific visualization with OSPRay materials. Here I just have a couple of really silly examples, but I think they are still nice just to show you that this is possible. So in this slide, I have a material that, a data set that I use all the time in teaching ParaView, and the file is called signenvelope .nc, so it's an SCDF file. You can just Google it. I'm sure you can find in one of the outstanding ParaView tutorials. And it's just a three-dimensional function that is discretized on a 100 by 100 by 100 Cartesian mesh. So I load it into ParaView, and then here what I do, I basically apply the contour filter, and then I see the contours and also the clipped volume, the original volume which is clipped, and then I'm showing them both at the same time, and then I just assign the OSPRay, so in this case I guess it's bronze material, to the contour lines, contour surfaces, and as you can see the result is really nice. So you can also assign another material, for example glass, and so here I created a short movie that will probably not play back nicely, but I'll try to play it back anyway. So I will see it nicely on my screen, but it might show with some delay on your screen, but it's just nice animation to show that this is possible. So here's the same visualization, but I have glass instead of bronze for the isocontour lines. And here I have a nice rotation. Let's see. Not sure if you see it on your screen, but it actually you have nice moving refraction and really fantastic effect. Okay. All right. So the next example also kind of silly, but still this is useful, I think. So in this case, I have this is a standard data set from ParaView and VTK tutorials that was created by ParaView folks, and the data set is called, I think the file is called diskoutdraft.x2, and here I'm showing the distribution of temperature inside this cylindrical object, and also I'm showing the velocity field with streamlines, and I apply the glass material to the streamlines. So the nice thing here is you can actually see the distribution of temperature through the glass streamlines because they are kind of transparent, right? And you have nice refraction of temperature distribution inside the streamlines. So the nice visualization, I think, the final visualization looks really nice. So complex scenes, when you apply photorealistic renderings to your visualizations, well, you want to do it to fairly complex, data sets or fairly complex scenes. And usually, when you do this, the vast majority of the work is actually creating these scenes, right? It's not it's not generating materials. It's not applying materials or applying lighting. It's lighting. It's really generating the scenes. So generating scenes is the hard work. And so whether the scenes come from numerical simulations, as is usually the case with scientific visualization, or they come from some sort of a design or 3D print tool or a 3D mesh generator, or perhaps it's live scan, an actual scan of a real three-dimensional object, or photogrammetry. So in any cases, you have this scene, and you have to make sure that everything is encoded nicely, all the surfaces are done nicely, and then if this is the case, then you can actually apply OSPRay materials to them. And so you prepare your scene, you define your materials, you define your lights, perhaps test your shadows with, without materials first, and then at the very end, you go into the path tracer, into rendering, and you actually render, which will take some time. So here I'm going to show you an example, a complex scene example. So I downloaded a three-dimensional model from this place called Sketchfab. So it's actually a very popular commercial hub for exchanging and buying, selling three-dimensional models, and you can find a bunch of free three-dimensional models there. So the one that I downloaded is, if I click on the link, it'll actually show you. Oh, right here, the link. It'll actually download the open the site, and also this is what the model looks like. The one I downloaded. Just a second. So it's a three-dimensional car, right, with a lot of different surfaces, tons and tons of polygons, etc. So I went ahead and downloaded this as a. So originally it was created in Blender, but you can also download as a GLTF file. So it's a newish file for very efficient encoding of scenes, and it also supports animation. So it's stored in JSON format, and so this particular scene is free under Creative Commons license. So you download it. And when you load it into ParaView, before you load it, you actually have to, so it's a GLTF format that is enabled in ParaView as a plugin. So you have to make sure that the plugin is enabled, and then you load the file. And then I apply it to different texture tools. So a car paint, and then this object black bright material. So let me show you what it looks like, and then I will show you the final rendering. So I will open ParaView. And then I'll go to Tools, Manage Plugins, and then I will enable this GLTF Reader plugin. Okay, now it's loaded, and then I will upload my state file that has the scene already set up. So load state, and then on my laptop it's a car PVSM state file, and then yes, just confirm the file paths, and then in a second we should see the rendering. And then here we go. So here I already switched to the materials, the OSPRay materials. And this is a nice rendering. So if I want to increase the quality, I will increase the number of samples per pixel. So for production work, I will do something like 30. And then all this noise will disappear. And if you want, you can actually, so if you want to make it interactive, you want to produce an animation, let's say, you would turn off ray tracing. So now this is, regular OpenGL rendering, right? Running on top of on my GPU, on my laptop, and it's very interactive, very fast. And then I actually color by this variable called UDK block color. So it's one of the multiple variables inside of this file that I downloaded. I mean the scene file, and it lets you differentiate between different variables. And then later on, when I enable ray tracing, I just switch to coloring by to categorical coloring. And so if I go to enable ray tracing, and then just wait a second, and then I go to edit color map. So here you see that I define different materials for different surfaces. And here we go. We have a nice visualization. And then if you want to make a movie out of this, it's really, really easy to do. You just use the same, the standard ParaView keyframe animation. And so next, I'm going to show you a movie that I created. Again, I don't know whether this will play nicely on your machine, but here's the movie. So in this movie, well, actually, let's watch it. This was done entirely on my laptop. It took about 79 minutes. And I have 300 frames at this 1812 by 1276 resolution with 5 samples per pixel. So as I said, it took 75 minutes using all 4 cores on my laptop. All right, so the final couple of slides is on parallel rendering and compute kinetic clusters. So as I mentioned before, OSPRay works really well with MPI, so that means that you can actually run it on multiple cores and on multiple nodes and multiple cores on each, so you can scale, to large number of processors. And to do that, you will have to use a version of ParaView on the cluster that was compiled with OSPRay enabled. And this is unfortunately kind of tricky to do, so the default installations don't have ParaView, and you have to have not only ParaView but also materials, and it's kind of a hack. I know how to do that, so I have a compilation inside my home directory on CEDA. So on CEDA, if you go to Home Razumov and ParaView CPU 571 is the latest version with OSPRay and materials I have compiled. So it's a server only. So that means that there is no GUI, but you can use it both in client server mode and in batch mode visualization. So here I have a couple of scripts. One is serial.sh. So this script basically submits in this case, it's 15-minute job, asking for almost 4 gigabytes of memory, and then I'm simply running pv batch, passing the same test materials.py script, then the name of the file containing the checker pattern, and also the name of the output file, right? So this will run in serial and single processor when you submit to the batch queue and to the scheduler, and then parallel.sh will run exactly the same, do exactly the same rendering in parallel. So in this case, I'm asking for 16 cores and 15 minutes maximum workload time. So the same, almost 4 gigabytes of memory per core, and then I have to make sure that I enable parallel ray tracing. So I use MPI run to schedule the ParaView Python at runtime. Okay? And these are, so my final slide, these are the benchmarks. And as you can see, you do get acceleration, but it's certainly not 100% parallel scaling. So you see that when, let's say with a fairly large job, so 100 samples per pixel, in serial it takes 6 minutes on CEDA, on a single core. Then when I go to 4 cores, it's almost twice as fast, but certainly not 4 times as fast. And then when I go to 16 cores, it's it's roughly 4 times as fast. So scaling is not ideal. I think part of the problem here is that I'm actually running a very simple visualization where I don't have a lot of stuff to do to each block, to each decomposed block running on a single processor, and then there's a lot of communication. So I suspect these numbers will change, and you will get better scaling as you go to more and more complex scenes, right? So your acceleration will actually be, your speed up will be faster on CEDA. So on Gram, Beluga, other clusters, we don't have ParaView with OSPRay and materials installed, but if you want this, let me know, and I'll be happy to install it in your own directory or tell you how to do that. Okay. So this is my final slide showing the summary. Basically, there is some documentation. Documentation is kind of difficult to find, especially for ParaView, for how to use ParaView, how to use OSPRay materials inside of ParaView. So OSPRay documentation is fairly good, I find. And then there are a lot of questions and answers on ParaView discourse, which I find is really, really excellent way to search for, for relevant information. And then there's also, there's a few months old presentation from October last year by the Swiss National Supercomputing Center by Jean Pava, and really, really beautiful 1-hour presentation on essentially the same topic, but with somewhat different examples. And then if you need any help, just email me at any time. I'll be happy to help you.